I recently volunteered to make a trophy for a health and wellness initiative, a factory-wide step challenge to be specific. The trophy I made isn't anything to write home about, no rocket surgery, just a few pieces of CNC'd acrylic and a 3D printed collar. However, a few friends at work suggested that adding LEDs would make the trophy pop, and I think that might be worth documenting. Only after I volunteered to make the circuit board did I remember that I've never actually made a circuit board. So this is me cutting a piece of copper-clad wafer for some quick experimentation. Put the wafer on the spoil board using double-sided tape. For my first experiment, I used a 30-degree engraving bit. I know that there are end mills sold specifically for the purpose of cutting PCBs, but I'm going to get away with a V-cutter for now. That orange foil is 1/1000th of an inch thick. Slowly descending the cutter until it pinches the foil onto the wafer will therefore help me locate the position on my Z-axis. So this is what you shouldn't do. That bit is moving far too rapidly across the surface of my workpiece, and it's really tearing up that thin copper layer on top of the wafer, really leaving behind an undesirable jagged cut. It may or may not conduct electricity the way it should, but, I think I can do better. But this is why you experiment. My trusty old Radio Shack multimeter is confirming that there is continuity where there should be and disconnects where there ought to be across the experiment, but the surface finish really leaves something to be desired, and I'm going to try again. I tried again. This time I used a 10-degree cutter and only moved that bit about 3 inches per minute. It took significantly longer, but the cut was just exponentially better quality, as you can see from this footage. And these are the settings I'm going to be using for the rest of the project. This is the layout for the PCB that we need for our trophy. It was designed by Octavian, a friend and coworker that you'll be meeting later in this video. I have a basic understanding of circuitry, but Octavian's layout is well over my head. However, I do know that Octavian's traces are pretty narrow. I'm going to attempt to set myself up for success by altering the design just a bit. I'm going to thicken these traces by 5/1000ths of an inch. That might not sound like much, but I'm going to need all the help I can get. After all, this is my first board. Just as with my initial experiment, I'm going to put the final piece down on my spoil board with double-sided tape. And here we go. You'll notice that the engraving bit is moving much slower across the workpiece this time than in my initial experiment. 3 inches a minute is painfully slow, and it actually took quite a while to do all the engraving on this board. I think in total it took half an hour to get all these traces cut. Although from what I've been told, half an hour to cut a board of this size, as compared to other manufacturing methods, might actually be considered rapid. Alright, that's it for the engraving. Now it's time to get the multimeter back out again and check to make sure all those little squiggles are electrically isolated from each other as they should be. And everything seems to be working just fine. Now I need to cut out those 4 little rectangles you see in the center of the board, as well as cutting out the perimeter of the board from the rest of the material. So I've swapped out the engraving bit for a very small, I think it's 1.5 millimeter end mill. And that's going to finish up this job for us. Well, that's it. Job's done. Time to peel it off my spoil board and get over to Octavian to be built into something useful from here.
Alright, the project is finished. I think it turned out really well. I asked Octavian to come down to my basement here and explain how it actually works, because although I understand the mechanics of it, the electricity is way beyond me. So without further ado, we'll take this thing apart and show you what makes it tick. Let's get this thing taken apart. The power supply itself is just an iPhone charger donated by our friend Lee, and all the other pieces are friction fit. There's a trophy face, this top piece of acrylic with 3 holes to accommodate 3 of the LEDs in the center. Same thing on the bottom without the holes. And then the 3D printed collar, which has a little lip on it right here for that board to rest on. And that is really as much as I understand. For the rest of the project, we'll have to kick over to Octavian.
Alright, so power comes in through this wire, comes from this little iPhone charger, and the ground side, the negative side of the power supply goes in right here. Positive side goes right here. The positive goes pretty much all across the board to a multitude of components, and then you get the ground that goes to a few other components over here. And these components, which you'll see on the other side, connect the power and ground together. So if you take a look over here, you'll see this. This is pretty much the brain of the whole operation, literally. This, as small as you see it, I mean, it's not even 1/4 of an inch, but this is a microprocessor. I mean, compared to what you have in your computer today, it's not even remotely as powerful. I mean, compared to the billions of operations per second that a modern computer can run, this can only do maybe like 10 million. But again, 10 million is all it takes.
And that's the bit that actually has the code on it that runs this gizmo?
Yeah.
And
this.
You wrote that code yourself?
Yep, that was all homemade, from scratch. It was a case of, hey, we have this idea. And I said, hey, yeah, we'll make it work.
How many lines of code are on that chip?
About 500 or so lines of code. And
oh yeah, that's it.
yeah, and 500 lines of code, which compile to maybe about 3.5, 4 kilobytes. In this day and age of like gigabytes and terabytes of storage, this thing just runs on 3.5 kilobytes. It can only store up to 8, and it only has like 2 kilobytes of RAM. So it's a joke compared to a modern computer, but that's all it takes because it's designed for real-time applications. It can do a lot with these little resources. And this little microprocessor here controls these 3 components, and they are called transistors. What do? They're switches. They pretty much, you can send a control signal to them from this little microprocessor, and they will just turn power on and off to these LEDs. And the way they do it, it's almost backwards, it's almost counterintuitive. Power always goes to these LEDs. The transistors actually switch on the ground side, so it's not the way you would normally do it, but it actually allows you to do it with less components, and it's more efficient. So these 3 transistors here, and the reason there's 3 of them is because these 9 LEDs are actually grouped into sets of 3, so these 3 LEDs are all controlled by this transistor. Then you have these 3 LEDs controlled by this transistor, and then this guy over here controls these 3. And these 3 transistors over here can be turned on and off really, really fast. I mean, we're talking about maybe 30,000 times a second. And because of that, although that's all they can do, there's no in-between state. There's no like half on or a quarter on. It's either on, full bright, or off. But
so what makes the LEDs appear to be dim or bright to us?
It's called pulse width modulation, because this little chip can turn those transistors on and off 30,000 times a second. It can actually say, you know what, I'm going to turn the LEDs on for maybe 1% of the time. So they're fully bright for 1%, and then they're off for the 99%. And what we see that is as an LED that's 1% bright. If you turn it on for 20% of the time and off for 80%, then you see it as 20% bright. They're never 20% bright. They're just like on and off really, really fast. And this little technique is called pulse width modulation, and it's being used pretty much everywhere today because it's the most efficient way to control the brightness of a light. That's how your light dimmers work in your house. That's how it works, in your dashboard in your car. That's how it works in your phone. It's cutting edge technology.
What are the capacitors for?
Well, good point. Because we're turning power on and off really fast, it also means that sometimes this little power supply doesn't have time to react quickly enough to the sudden power changes. You know, all of a sudden, you know, you're pulling 5 or 6 or 10 watts, and then half a millisecond later you go to nothing, and then another half a millisecond later you go back to full power. So what would happen is the voltage would actually sag, you know, and then it would increase again and sag again, and this could potentially upset that microprocessor. The processors in general don't like, you know, voltages that go up and down. It can actually reset them, cause them to hang up, or do other things that we don't want them to do. So these two capacitors here store energy. So for that little, like half a millisecond or less that it takes for that power supply to recover from that power surge, these things store enough energy to keep the microprocessor happy, and also to keep the LEDs happy, and make sure they don't dim down and then brighten up and cause other issues. Also, you'll notice there's some resistor on the board, and think of these resistors pretty much as current limiters. An LED, which by the way stands for a light emitting diode, an LED, if you just connect it straight across the power supply, it will pull so much current that it will just burn up in a couple of seconds. So you need those resistors there to limit the current, because otherwise they turn from LEDs to DEDs, or dark emitting diodes, which serve no useful purpose in life. But if you actually go online, you'll see quite a few papers on them, usually published on April 1st. Also, right here under this LED, and you can probably see it better here, there's a switch. And that switch is being read by that microprocessor, and it will tell the microprocessor to change mode. So this trophy has about 8 different modes, you know, different brightness, you know, lights, you know, lights that go up and down, lights that turn in a circle, and all these modes are switched with that little switch in the back. Also, if you hold that switch when you power it up, you can enable a random mode, which will just run through all these modes randomly, you know, for different amounts of time, and it makes for a good display case.
All right, well, let's put it back together and fire it up, and that should close out the video.
All right.
Okay, Octavian, turn it on.
All right. Let's plug it in, and this is it.
Ta-da! Works well, thank you. Kind of makes me wish we'd actually enrolled in that contest.
Well, there's still time.
No, I don't think there is. Thank you, YouTube. See you later.